Good morning. It's Sunday and we are live to Cosmic Talks. And Cosmic Talks, this is Cosmic Talks episode 4, in which we are going to talk on a very different, we can say, perspective on singularity. So we are going to get live with Ronrick Alexan. He's my mentor from years and he has taught me so many stuff about Nova physics. So let's first ask him to join. Um, yep, I've sent him an invite to join. Yes, who is awaking right now? Okay, someone's awake at this time in morning. That is really good because it's Sunday and I was hoping that nobody will join today, but people are joining, so this is good. All right, so we're going to talk about all right, yes, we are going to talk about the singularity in a very different perspective. The teacher is from he's doing research on cosmology, the plasma cosmology, in which he has made an entirely different perspective from what we have right now. We believe in singularity, that everything will come up to. Just a moment, he has joined. Just a moment. Join. I think there's a problem with him joining the session. All right. So talking about Ronrick Alexan, he is a self-taught person and he has inspired me to this way to uh, to learn physics by myself, and he is telling me the importance of learning by myself. Okay, let's just wait for him for a while. Just a moment. I think there is a problem with him joining live. Let's just I'm having connection difficulties. Zoom is having some connection difficulties. I'll send you again. I'll send you again. I hope it will join. Okay. We hope we can join this time. Oh, finally. Hello.
Hello.
Hello, sir. How are you?
I'm doing fine. Hello.
Sir, can you please switch on the lights?
I cannot. I'm outside right now. If I go in, it'll be very loud and distracting. I have no better place to be.
Right. Okay, no worries. So here, I would like to know about the singularity that you are working on.
Yes, ma'am. Where would you like me to start?
Um, from a very basic so that we can understand.
Very good.
Yes.
My my view on singularity is basically as a mathematical construct, it works fine, but when we take that construct and then try to put it into the objects that we find in the universe, we see inconsistencies. There are things that don't match up with the explanation or with the physics that black hole says versus observation. There's inconsistencies there.
Okay, so we cannot find that observations are not like what we have explained through theories, right?
Well, the objects in the universe that are supposed to have black holes would be, say, like supernova and galactic cores.
Can you please repeat it?
The objects in the universe that are supposed to create black holes, I mean, the conditions, that create black holes and the objects that are supposed to be are associated with supernova and galactic cores.
All right, so
And
instead of black holes, it should be supernova.
well, when supernova occur, it gives it enables conditions to enable Schwarzschild radius. This is what we're talking about.
Yes.
The solutions of Einstein's equations that wind up creating black hole, to the extent where it takes faster than the speed of light for escape velocity, that boundary is Schwarzschild radius. And
Yes.
in the universe, we have conditions that create this all the time. Now, modern theory says that those conditions should create black hole, but there's conflict in observation with that. For instance, within supernova,
Yes.
the problem there is we have an issue with the power source. When stars collapse and they wind up achieving Schwarzschild radius, at that point in time, the Schwarzschild radius is supposed to be a boundary. It's supposed to be the inside of a black hole. It's supposed to be something where nothing can, escape from.
Yes.
It's, it's game over as far as, any activity coming out from the core. But what we see in the universe is a very energetic explosion. And that explosion is usually explained by neutrino interaction. Now, it is
All right.
known within physics that neutrinos are very weakly interactive. We can barely catch, a few of them at all. It would take 4 light years of lead, like an extent, from here to the closest star of solid lead to reliably catch a neutrino coming from our star. That's how weakly interacting they are. So the explanation in modern physics is that these neutrinos, for some reason or somehow, have managed to have enough interaction within the core of a star to blow it apart and to essentially outshine its own galaxy. I mean, that's the explanation. And it is a
Yes.
very, very weak explanation. I mean, you can't do
That
that.
there-
The physics actually doesn't support it.
All
The
right, so the neutrinos cannot do that.
neutrinos cannot do that. And that's the
All
only
right.
explanation that they have. Because again, when we have very large stars that will achieve Schwarzschild radius upon collapse, that's a boundary. I mean, we can't,
Yes.
get anything out of that, anymore. Except for apparently neutrinos, which is a shady story to begin with. But so yeah, that's the status of modern theory, and it's insufficient. Not only, yeah, it's insufficient.
All right. I remember that you once told me that those light that outshines the whole galaxy, such kind of energy can only be generated from supernova.
Yeah, that that is created from supernova, but
So
the
what else is your
process
explanation about it?
the process as I see it is it's reverse. When modern theory has it that when we achieve Schwarzschild radius, everything is supposed to be sequestered. It all goes, everything, the whole system collapses into singularity, and it's over. You have a black hole. And what I believe is the exact opposite of that. I think that the particles get released from particle state into pure radiative energy as per E equals mc squared.
All right.
And observation supports this as well, because now the story behind supernova changes dramatically. Now it's not a matter of, okay, we achieve Schwarzschild radius and now there's a boundary that we can't pass, and maybe neutrinos, can blow up a star somehow, when it takes 4 light years to, reliably stop one. I mean, it's a ridiculous story. It's nonsensical. The modern physics, that story is, I don't know. But now the story becomes, with the E equals mc squared approach to redefining nova, we wind up with, we achieve Schwarzschild radius, and now everything within Schwarzschild radius is radiative energy, and that radiative energy is going to want to go somewhere, and it goes straight out, blowing up the star and enabling it to indeed outshine its own galaxy.
All right. So that it is just getting, it will just blow up. That's it. Nothing else would happen.
What do you mean?
I mean that whole matter in the star that will just blow up. That is equals to mc square. Like it will all blow up, and that energy that is converted from the mass will outshine the galaxy.
Yes and no. Yeah, that's what happens. But whether or not it all blows up, that's a different story. Because I mean, we like to base our models on very neat and simple things. When we collapse a star, we make it collapse in a sphere, or concentric spheres, and it doesn't happen that way in the natural world. Nothing happens in perfect little spheres. In fact, when we look at gamma ray bursts, and we have information from that, from the Swift observatories and Fermi satellites up in orbit, but when we look into those gamma ray bursts and their signatures and how they come about, that tells us everything we need to know about how Schwarzschild radius is actually achieved. Because gamma ray bursts are the signature of nova. That is the signature of Schwarzschild radius and how it's achieved. So what we see within those signatures is it doesn't just collapse down into a perfect little ball, or a perfect little spike in the signature, and then gradually falls off, as we would expect if everything would go concentric, if everything did collapse in idealistic ways. But it doesn't. What we see is spikes and dips and weird things, and some signatures, have very different profiles than the other signatures. And what we can infer from this is some stars, they blow up smoothly. Some stars, sure, it is more of an idealistic, concentric collapse, and some stars it's not, it sputters. It looks like Beetlejuice, a little plow there and a plow there, and, doing all sorts of weird stuff. So in nature, no, I mean, it goes all sorts of different ways. Sometimes some things will blow themselves apart and leave nothing but a nebula as a remnant, and other things are going to leave things behind, so
Can you
it's
just
hard to
repeat
say.
it? Well, can you just make it quite simple to understand? I cannot just completely understand what you're trying to say.
Well, what I'm trying to say is that some stars will wind up completely blowing themselves up,
Yes.
and leaving nothing but nebula behind, whereas other,
Yeah.
explosions, even if they have the same mass, and same characteristics
It
outright,
depends on the
they're
mass.
um, just just miscellaneous. I mean, some stars will wind up leaving remnants behind because because the point behind that is when you look into the signature of gamma ray bursts, which is the signature of Schwarzschild radius. I mean, that is how we get those signals, and like I said, it's not a smooth picture, it's sputtery, so we'll wind up with, in nature, it goes haphazardly, it's not smooth, is
All right.
just
So, yes. Rose, I just got a bit confused. Hello.
about what? About
Um,
what?
not like it's. I think you are telling that all that depends. All stars will not just blow up. It depends on its mass. That some will go. Some will go and will end up into, like, some will just blow up, or someone will just end up in another kind that is white dwarf or black dwarf, or another will just leave behind nebula.
Mm, okay. Oh,
So, is that what you're trying to
you
say?
froze. You froze on me there for a moment, but yeah, it's just not a smooth process. All stars will do their own thing, is basically how that goes. But the
All
but
right.
thing about that, we can see it. We can see it in the gamma ray bursts. The signature that they leave behind us tells us exactly how Schwarzschild radius is behaving. That's the point of it.
All right. So basically, talking about Schwarzschild radius, what, according to you, how it is behaving?
How is it behaving? Haphazardly.
Sorry?
well, well, haphazardly. Again, it doesn't. When we think of core collapse, we might think of a perfect little core collapse, just the ball itself going in just shrinking down.
Hmm.
In
That's
concentric,
what we imagine.
that's what we imagine, but that's not what
Yes.
happens. Like I said, when we look into the actual signature, I mean, what Mother Nature is telling us about achieving that, what we find is that no, the signature is all over the place. I mean, sometimes we'll get a lead spike initially, and sometimes the major spike happens later. So that's telling us is that Schwarzschild radius is not happening in perfect little concentric balls in the core. It's happening in here and there, and within regions, in the
All
area,
right.
basically. And we got to keep in mind that this isn't just a static ball either. I mean, everything within it is moving. You have electromagnetism going all over the place in there, and you have
All right. All right. So
convection cells. I'm sorry.
what we imagine that the whole ball is perfectly just shrinking, but we didn't imagine any that process going on inside the ball. So it will be like everywhere there will be small collapses, right?
That again, my connection's getting weird again. I'm sorry.
All right.
I, I
Uh, we imagine, until today we have imagined that the ball that is the star, it will collapse. It will collapse and will be shrinking. Just in, like, if from whole it will be shrinking, but it's not the case. There will be collapses inside the ball. Like, it is not completely, we can say, uh, very smooth, not smooth, but it does not have matter all over the places. It will be there will be small collapses everywhere inside the star.
Yeah. Well, I mean, within the core region, but the thing is, the core itself isn't,
Mhm.
going to do it all at once. I mean,
All
it's
right, it
not
won't
smooth,
get all
even
into
in
one
that
space.
action. Yeah, it
All
won't,
right.
not all at once.
Okay, so that's not good. Then what after that? What next? What is the next?
Um, well, we have core collapse. We achieve
Mhm.
Schwarzschild radius, and
Yeah.
then the schools of thought are either it blows itself apart because it turns itself into pure radiative energy at that point, and
Mhm.
there you go. which is the nova approach, or it turns into a black hole, and we're not really sure. You know, the story gets, a little less scientific at that point. I mean, there's no physics behind it. You know, there's
All
no
right. So
math.
what do you think about black holes and the image that we got?
What? Oh, the image. The image is of an accretion disk. You're not seeing a black hole in that. You're seeing an accretion disk. What's inside the accretion disk is up for interpretation. And again, that interpretation depends exactly on, what your take on that is. The thing about Schwarzschild radius is it's about the size of a neutron star to begin with. When you get a neutron star that is on the threshold of achieving Schwarzschild radius, like, it's not going to grow any bigger. I mean, that essentially is, the volume of Schwarzschild radius, and furthermore, like, you wouldn't be able to tell the difference observationally. We wouldn't know if that was a neutron star or not. It has the same mass. The radius of it is the same mass as a black hole would be.
Yes.
So all we saw there. I'm sorry.
So it might be. It cannot be a neutron star.
No, it can be. Oh yeah, it most certainly is. Yeah, no, because we didn't see a black hole. All we saw was the radius of it. But that radius is exactly the same as a neutron star.
All right.
And what's inside of it? All we saw was the accretion disk.
Yes, we just
inside of it was interpretation. And again, observationally, we could not distinguish between the two. We can't, because of the same mass. A black hole of the same mass is going to have the Schwarzschild radius. The event horizon is going to be the same size as a neutron star. The physics just works out like that. That's how the math plays out.
All right, so I got this. All right, then I would like to ask you that what is your next approach? I mean, what are you going to do next now? As we you have already done this. You think in terms of everything. You have we can say you have make a theory. Like, what next are you going to do?
Publish it, get the math tidied out. I'm still toying with the mathematics in on the QM end of things. Gravitation isn't challenging, just modern physics. It's an interesting one for me as well. Nova is definitely, working on that one still. So yeah, but no, just tidy it up, publish it.
Okay, so I have already studied your theory several times, but still it is I get the ideas clear, but it's still quite, I have to think a lot about it to get it into it, or I have to think a lot about it. And even though I understand, it is quite hard to explain it. I can explain it in a simple words. What I have understood from your theory is that singularity is not going to happen. There will be a Schwarzschild radius. There will be a Schwarzschild radius, but in how can I explain this? I'm told it's quite difficult to explain what you were trying to say me. All right, what I have understood from this is that that star will collapse into an explosion. In explosion, it will blow up all its mass instead of having a singularity point, because that singularity point is not practically possible, right? And we have not observed it.
Well, it's mathematically possible. I mean, it looks good on paper. It's self-consistent and it's fine. The problem is when we use that model in place of what we see in the universe, inconsistencies arise. The universe doesn't, do the same thing as that. So when we flip the story, I mean, yeah, we achieve Schwarzschild radius, but instead of making that mean, everything goes away, we just make it mean E equals mc squared, instead of it being, mass at that point in time, as what we can infer as particles or whatever. Now we just turn it into radiative energy. And as soon as we do, that's the distinction right there. I mean, it's a redefinition of nova. It's a change of state, once you achieve Schwarzschild radius. So you achieve Schwarzschild radius, everything within turns into radiative energy, and that's how, everything
Then
blows
what is
itself
left
apart.
behind? What is left behind?
That depends, like we were just discussing about the gamma ray bursts and everything, that the
Okay.
signature of gamma ray bursts is the signature of achieving Schwarzschild radius. That's how the universe produces those signals. So
All right.
when we look into those signals, it gets weird. What's left behind? Sometimes nothing. Sometimes it's just a nebula. Other times we will find bodies behind, including neutron stars.
Okay. And what about the Hawking radiation? What is your explanation for that?
Hawking radiation. Yeah, I don't feel very highly about that. See, for one, Hawking radiation assumes at at the event horizon, at Schwarzschild radius, that it's going to separate particles that come out of the foam, the
Mhm.
background, foam. Well, it's a quantum electrodynamics, right? It's Feynman's work. So we have this
Yes.
foam. We get particles and antiparticles, coming out of nowhere and self-annihilating, on the spot, all over the
Mhm.
place. That's just the nature of the background of the universe.
Sorry, what?
As per Q, that's just how modern physics is, you know.
I'm sorry, I
Um,
didn't get you.
I said that's just how modern physics is, the background self-annihilating particles, right? The
Yes.
background foam, as it's called. Okay, so at Schwarzschild radius, though the story goes for the Hawking radiation that it takes the antiparticle, right? Only the
Hmm.
antiparticle, because it leaves the real particle behind and enables the real particle to shine on us. So it's arbitrarily picking the particles that they want to pick. At Schwarzschild radius, if there was such a thing, if it was legitimately true physics, what you would find is an even spread. What we would find is that we would have antimatter and matter particles coming out of that radiation at equal proportions. It's not just going to be the matter proportion. I mean, physics, the event horizon has no way of determining and choosing which is which. So that part of the Hawking radiation story is faulty. You can't do that. Physics does not do that. Mother Nature does not do that. Um, so, you can't choose the type of particle because, and furthermore, you have to do that. As far as the theory goes, you have to do that because if you didn't, what we would find in observation is that we would have anti-matter particles now free from their pair that they self-annihilate from, and now they're going to annihilate with stuff in the event horizon area, in the accretion disk, right? So if that were occurring, we would see antimatter annihilations all over the place, all the time. So we know observationally that cannot happen. So in order for
Okay.
Hawking radiation to work at all, they have to sequester it to just the matter particles get free. And so, again, there's a problem at that border. It's not going to just choose the matter particles. Furthermore, when it does have the antimatter particles, okay, that's fine. Antimatter particles, but antimatter particles have real mass. It's legitimate mass. It's the same kind of mass that we possess. It's not negative mass. Now, how does
Mhm.
legit, real, authentic mass get to the singularity and all of a sudden reduce its weight? It doesn't. There's a weird story in that too. And what it's doing is it's not only arbitrarily choosing the antimatter, but it's saying that antimatter now has negative mass, such that it's going to reduce the weight of the black hole. It's a fantastic story and it fits well within the mathematics of prevailing physics, but it's not relevant to physics at all. I mean, not to the physical reality. That is arbitrary and faulty all the way through. I mean, it looks great on paper. It's self-consistent, sure. I mean, it is not like it's an error in the math because it's not an error in the math. It's just wrong. It's just math that doesn't represent our universe is all.
All right. So, all right. I told you it's quite hard to understand what Which you're trying to
I'm sorry.
say.
And I talk fast when I get excited about physics too. So
Yes, yes, when you get excited about physics, you are going. Yeah, but
well,
I quite
the
understood this that it will the if I have to tell, then it will, the particles that the matter particles have to release, it won't release for like once and then will stop. It have to release like constantly, and we there are only matter particles which are releasing. So if that was really Hawking radiations were there, there will be all kind of particles would have been releasing from that, right? Which is not
uh,
which is not going there. So we like
well,
you, that particle has to choose, like we can say black hole has to choose which particle that
yeah,
it wants to release,
yeah.
and that is not possible.
Black black hole can't choose. That's right. It would have to be even. It would be even antimatter and matter. And if that were happening, we would see
Hmm.
annihilations. So we know that's not happening. Observationally, that we rule that out already. So yeah, that's the first problem. And then the second problem is turning that into negative mass. Such that it
Negative
reduces
one.
the weight of the black hole, the mass of the black hole, which is just plain silly.
All right, got this. So in and on you have, so like on you are going to make this big breakthrough, and you are going to build up a theory which is, I don't have words to describe that how it is going to be, and this is going to be very huge.
No, well, I don't know. I'm just a geek, who's gone far enough to share notes. That's all.
And I'm very what we can say, lucky to I have learned this throughout these years, and still I got so many problems when I read that book you sent me. I read some of the pages, and I was like, yes, in this book has that like the way you talk, and the things that have been represented in this book, that the way of talking, like how you represent things, it is quite similar.
Nice.
Yes, I just marked that yes,
Well,
he explains things in this way only.
nice. Yeah, no, that book that you shown and that I sent you, that represents the second generation of plasma cosmology. That is
All right.
basically, because the first generation happened way back when, it originated. The grandfather of this theory is Hans
Hmm.
Alfvén,
Yes, I know.
Nobel laureate from Sweden. So, he's the one who first applied plasma physics to space sciences and said, what? This stuff is everywhere. We see galaxies out there. I mean, there's energy conduits in space everywhere. Um, and then we have the works of Eric J. Lerner, contributing, the author of that book, but primarily Anthony Peratt and others out of the Los Alamos National Laboratory, United States, is New Mexico. But yeah, he's a plasma physicist, and he produced, the second generation, basically, I mean, him and colleagues, was working on the second generation of plasma cosmology. And that's what inspired Lerner to write the book that you're going to have,
Yes,
he's
it's
basically
very
talking
right.
about that. Yeah. So that book changed my life. I read that
Yes,
about
it is
20 years
actually.
ago, and it turned me into a plasma cosmologist. And from there, I developed NOVA. The NOVA includes changes like the singularity. It takes a different stance on what time is and how time dilation arises. It's an adjustment to relativity and quantum mechanics as far as that is concerned, and completely refutes Big Bang. Is the status on that. But yeah, no, originated there. And, again, that's a take on the
So, do
second
you believe
generation
in
of
Big
plasma
Bang?
cosmology. I'm sorry, say again.
Do you believe in Big Bang?
No, no.
All right, so
Uh,
you believe in infinite time.
yeah, yeah. And that comes from the book. That comes from just plasma cosmology outright. because when you
So,
look into the physics of plasma cosmology, what happens is
mhm,
it does not lend itself to any previous states. Whereas relativity has kind of a beginning built into it, plasma
mhm,
cosmology says no beginning. That's what's built into that. And then taking a step forward, some of my work, some of Nova, clarifies that
mhm.
situation by saying that time itself is actually it's a property of particles. It's a property of all the little particles that we're made of. It originates within our own physicality.
Yes, yes, I
It's not
remember that.
not Yeah, it's not tied to the universe as a whole. So Nova clarifies that by stating, the universe itself exists independently of time. It's not associated with time at all. It's only you and me and all the energy in the universe that experiences it. It originates from its dynamic, as far
All
as that
right.
goes.
So, do you think it is possible that Big Bang is just, you know, what we can say, a small, a kind of like universe was there
Um,
before Big Bang, and it was just a small gas from where we have came. Is that possible?
um, Maybe, you know, but no, not to any large extent. I mean,
Hmm.
the plasma, the filamentary structure of the universe, that web that's out in the large scale structure of the universe.
No.
Okay. So there's basically the large scale structure of the universe is formatted in like a web-like structure. You have filaments interconnecting all over the place. Now, within um, when you get a spiral galaxy that's got a black hole, or not a black hole, but it's got a neutron star in the center of it, that's on the verge of achieving Schwarzschild Radius, and you dump any stuff on that, what's going to happen is it's going to create a galactic jet. I mean, it's the extra energy, as far as within Schwarzschild Radius, most of that energy goes out the poles, as we know.
Hmm.
Those are the brightest spots, and it's because that's the weakest point in the magnetic field. Magnetic fields holding most of the structure together. So they're going to create jets. Now, when you dump a couple of galaxies on top of each other, um, Schwarzschild radius winds up growing and growing faster than radius of the neutron star it's housed within, right? So there's a point where neutron stars could blow themselves up if they get on top of each other. um, so you merge two large galaxies, two elliptical galaxies or something like that, and yeah,
Hmm.
the by the time they merge, they will
They would blast it like
the
that.
they will, yeah, because the physics of it. I mean, Schwarzschild radius just grows faster within the radius than the outside, would from any star that's collapsing like that. And because of that, it can become rather volatile. And because of that, it could reformat
Hmm.
a filament, basically a localized region. I mean, we're talking the size of a supercluster or so. But the any kind of big bang, beyond that, beyond, interpacting or impacting like superclusters, no, no, wouldn't happen. And furthermore, what we perceive within how modern physics reads redshifts
Hmm.
is not always the same as how they manifest. We have demonstrations of this in a couple of different ways. The book gets into it. You'll wind up seeing that rather soon, I imagine. You know,
All right. What are you talking about, Redshift?
um, well, the way Redshift happens,
Hmm.
is different from how modern theory processes it. Because
Sorry, what?
modern
How
theory,
long?
modern physics thinks that
Hmm.
redshift is a matter of Doppler effect. Whether or not it's coming
Yes.
or going. That's
Hmm.
largely how it goes.
Hmm.
And every now and then they make accounts and or make allowances for a little bit of redshift around stars, and everything like that, due to, gravitational lensing and whatever. But
Mm.
it's just an afterthought. It's not really, looking into it legitimately. But what we find in the universe is that we have structures out there that have greatly varying redshifts. What that
Right.
means, I mean, as far as modern theory interpretation goes, what what that would mean is that we have, points within a single structure that are not associated with each other, that they're, just a line of sight, and that we have one in the foreground and maybe another piece in the background, and, a few more even behind that or something. But, you know, pardon me. But the interpretation of these greatly varying redshifts that we find is that these, this single, or, pieces of this single structure are of great distances from each other, that they could not possibly be pieces of this single structure, and yet they are. I mean, everybody out there is welcome to look up NGC 7306. I don't know, NGC
Uh,
7603. I'm sorry,
yes, yes,
but
what's that?
it's NGC is it's the catalog of star, and
Okay.
nebula and everything like that.
Mm-hmm.
But there's one of those nebula, and it's called NGC 7603. And what it shows is four quasars, and those quasars all have greatly varying redshift values, and that's not accounted for in modern theory. That's the point. What
Okay.
those values are supposed to be is Doppler values, and that's of course supposed to be proportional to, the Hubble constant and Hubble
Mm-hmm.
law and everything. So when we see, a redshift value that's slight, okay, that's really close, and then moderate, okay, that's kind of, far, and then, a really extreme redshift value, okay, that's very, very far. I mean, that's how
Mm-hmm.
we're supposed to read them. But we have, again, like I say, structures like NGC 7603, and then NGC 4319 is another structure, very famous one, that was a point of conflict there for a little while. And we have many of these structures that all have greatly varying redshifts. Quasars in them, spit out, different signatures, and should be, according to modern theory, disassociated with each other, but they're not. So modern theory is reading too much into redshifts and then thinking that the universe is expanding because of that, and it may not be. They're interpreting something wrong in there again.
So due to varying redshift, we cannot really predict that is that expand that because of the varying, what we can say, varying redshifts, we cannot really say that that it is really expanding or not. We are not we are not getting into right process of seeing that whether it is expanding or not.
Yeah, precisely. All that we can say right now is that we're not evaluating them properly, and
Yes.
that we're getting more redshifts out of the universe than, we already know.
Okay,
We're
so
getting
getting
more
more
redshifts
redshifts
because
doesn't
it's a
mean that
matter
the
of gravity.
universe is actually expanding.
I'm sorry?
Getting more redshifts doesn't mean the universe is expanding because we have varying redshifts.
Because we have gravitationally induced redshifts, so
All right.
those aren't being accounted for, by modern theory, and because of that, yeah, they have extra redshifts that they have to account for, and that lends itself, to the expanding universe. But, not necessarily. I mean, again, it's interpretations, and if your interpretations are wrong, then so is your theory, basically. So yeah, no, I don't believe in the expanding universe at all, and in fact, I see, that there are gravitational induced redshifts. I mean, that's why we have, these quasars that are spitting out different values, is because of different, masses and everything. So yeah, when we take that into account, the expanding universe goes away.
All right. So that's how it is. We need to learn a lot about this yet. What is universe is spending? Just a minute. Someone has just comment that your voice is really nice. So you should give your voice document. It is
Uh,
compliment. Someone has
Oh,
said that your
nice.
voice is really nice, so you should give it in documentary.
Nice. Well, thank you.
Yeah. Alright, I think the time is, yes, it is. Okay. So like this was completely fine experience, and I mean I have tried to learn so many things from this, but still has a really long way to go and have to learn a lot of things so that I can completely understand Nova. And I am trying to do that so that I can understand this theory fully. I hope I would be able to do it one day.
I have faith in you.
And,
Yeah. And
yes,
not
I
going to take
hope
you
I will
very
do it. Yeah, it will take really long as the base is quite weak to understand all these, you know, all these theories quite well. I'm right now going with relativity and quantum physics, which is quite hard for me to understand in very, we can say, on some level, it is quite hard for me to understand. But I hope that it will go. It will. I will do it anyway, and I'll definitely go on with Nova. And I hope you can have a, you can publish this theory with maths really soon, so that you can be superstar very soon.
Yeah, yeah. Well, I've been sidetracked right now. I have a different work I'm trying to publish, but as soon as I get that wrapped up, absolutely, Nova Theory is what I'm working on. So yeah, yeah, probably a decade. That's my guess. Give me a decade on that.
Decade.
Yeah.
Yeah, but you are going to rock. That's going to happen for sure.
Nice.
Yes, so I think this time is going to, yes, it will end very soon. So it was really great talking to you, sir, and it was like my privilege to talk to you. Someone has just astronomy in one word. Could you answer him? Astronomy in one word. All right. Oh, he has already answered love. Forget it. All right. So, um, okay, fine. It was a really good to talk to you, and I'm so blessed that I have teacher like you, and it was completely and very good experience to talk to you on a platform like I have been learning from you since years now, and this is really good. This was completely fine experience for me. It was excellent experience for me. Thank you so much.
You're very welcome, and thank you again. It's my pleasure to be here. And again, I like Sharon. Thank you for hearing me out.
That's what I love, because you tell something that is completely different. It has different perspective, and it creates so many questions in my mind. There are plenty of questions in my mind when you talk about things like, okay, this is like this. First of all, I have to understand it, and then while understanding, I have so many questions, and that things gives me what we can say. It just excites me in my own way. It excites me that okay, this is new, and this is going to be like. So I just I cannot explain that, but I really like it when you explain such things in a very new way. It's quite hard to understand, but I hope I will do it in some years, I guess.
I doubt it'll take you that long. Once you get through the book, you'll understand the basis of Nova,
Yes, yes,
and
that I'm
then
trying to do.
no, Nova's just you know, an, I don't know, an elaboration on top of it. So yeah, no, I have a lot of faith. You're gonna be able to put it together, no worries. And thank
Thank
you for
you.
having me here. It was a great pleasure. I appreciate it.
Yes, thank you so much. Sir, last question. Someone is asking, please someone is asking, what is astronomy for you in one word?
What's astronomy in one word? Wow.
Yes.
Only one word I could think of is love. I mean,
Yes.
because it's exploration is what it is. It's
Yeah, it's
exploration.
exploration, it's love.
Yeah.
That's okay. I would also tell it in word as well. Love. That's what
Yeah,
I would
well,
think of.
that's a personalized answer right there. But yeah, no, I think exploration is a fine way to go about that. So
Yes.
yeah.
All right, sir. I think this live will end in some minutes. So it was great talking to you. And once again, thank you so much for like letting me do this. Thank you so much, and thank you so much for every years that you have like. So thank you for so many years you have uh, you have you have explained me a lot of things, and I'm grateful for everything you have teach me. And
You're very welcome.
yes, and for the book as well. I love this book.
Yeah, no, I hope you get a lot out of it. I certainly did.
Yes, I'm definitely going to read this. I have to read this book for I guess 3 or 4 times to understand it completely.
Nice. Well, I'm looking
Yes,
forward to that. And yeah, do keep in contact with me if you
I
know
will
want any help
definitely.
walking through anything in there. Because I
Yes,
researched
sure.
it thoroughly when I got through it myself. I didn't trust him on anything. So anyway, that's how that went.
Okay, that's what I'll do as well.
Yeah, very good. All
All
right.
right, sir.
Well,
So thank you so much.
have a good morning then.
Sorry?
I said have a good morning then.
Oh yeah, and good evening to you at the last. Hello. Hello. I guess the connection
Yeah.
is lost. Yes, okay,
Oh,
sir. So let's
it's coming back. There it is.
end this live, and I hope we can do this once again with some another topic in quite detail.
It sounds great. It sounds great. There's definitely more
Yes.
to Nova we could talk about. So sure.
Yes, we can definitely arrange a live only on Nova so that everybody else can understand it as well.
Very good. Maybe I'll find me a
Yes,
better
okay.
Wi-Fi connection next time.
Yes,
Sorry about that,
sure.
guys.
Yeah, no worries. Right, sir. Goodbye.
Uh, my only contribution on string theory is I don't support it. Sorry. Just not
Okay,
saw the
okay, so
comments.
oh yeah,
Anyway.
string theory. You don't support string theory. Sir has a
No,
very
no.
different, or we can say, views on particles. Yes, so we can do that. We can arrange a live on particles.
Sure. Yeah.
Yes,
Well,
that
that'll
theory of
segue into
Noah.
time. So we could probably organize
Yes, it
something
has
about particles
time.
and
Time
time.
is I remember time is what we can say just like momentum, as particles have momentum, electric or like charge, in the same way they have time, right? According to Noah.
Mm, that got
In
garbled. I'm sorry. My connection's so poor. I didn't actually get that through right.
all right, no worries. We'll do it next time.
Okay. Perfect.
All right, goodbye.
All right. Good night. Good
Bye,
morning.
good night.
Good night for you.
Yeah.